I can't resist using a really interesting application of matrix inverses to review what we've seen so far with matrices. Okay, and then later on today we're going to do Markov chains. But let's start reviewing what we've seen we can do with matrices.
If you don't start making more sense, we're going to have to put you in a home.
Okay, I hope you remember that we can represent a relatively complicated system such as this, or even more complicated systems, with matrices. We have our coefficient matrix here, as you can see, and we can multiply that by what we call a variable matrix, and it'll equal the constant matrix. Now, let's check it. I want to show you that this really does work. This multiplication of matrices does represent this system. Remember how to multiply matrices? We start with the first row of the first matrix times the first column, or the only column in this case, of the second matrix. And son of a gun, 1 times x, 1 times y, and 0 times z. It works, doesn't it? Then the second row times the first column. And of course 0, x, is just not going to show up. Then we have 2y and minus 3z.
You are correct, sir.
And there it is. And 3x plus 1y and minus 1z.
Oakley did.
There we go. We got it. Okay? So you can see that this multiplication does represent this system. There's the coefficient matrix, and we're multiplying it times the variable matrix, and it's equaling the constant matrix. Now, do you remember why we did this? Well, if we can find, which the calculator can find, the inverse of a matrix and multiply both sides of this equation by that, that gets rid of that, and we have our answer. Because A inverse times A equals the identity matrix, or you might think of it as 1.
We went from good to sensational.
And how useful was that?
Now I use my secret weapon.
Okay, well, let's input these two matrices, the coefficient matrix and the constant matrix, into the calculator, and we'll get an answer. Okay, let's turn that baby on. And recall how to do that? Well, we have to hit the matrix button, which on the TI-83 Plus is going to be second x inverse. And I use edit, you may remember. So I'll cursor over to edit. And I'm first going to put in matrix A. So I'll hit enter to select that. And either overwrite or just put in that this, of course, is a 3 by 3 matrix. So 3, enter, 3, enter. And it makes room for me to put in this matrix, which I'll do. The first row is 1, enter, 1, enter, 0, enter. Then it jumps to the second row for me. So I'll put in 0, enter, 2, enter, and negative 3, enter. And then it jumps to the third row nicely. 3, enter, 1, enter, and negative 1, enter. Now recall what I have to do to get out of here. I got to quit. So second mode is quit. And it now remembered that matrix as A. I'll put the constant matrix, which is a 3 by 1 matrix, 10, 4, 6, in as B. So let's go into matrix again. Second inverse. Now I got a cursor over to edit first. And down to B. And this is a 3 by 1. So 3, enter, 1, enter. And it makes room. So it'll cursor amongst them for me. I'll hit the first one, 10, enter, then 4, enter, then 6, enter. And let me get out. Second mode, or quit. Okay, now it knows those, and I've put them in. Remember what to do now? Well, you'll use your names menu under matrix to type in A inverse times B, and it'll give you the XYZ matrix. That's what you should get, and that's X, Y, and Z.
You just want to be...
Not too shabby. Let's do it. I'll do it for you just to make sure that you recall how to do that. I'll go into the matrix menu, second inverse, and I'm going to stay on names this time because I'm going to be referencing them, and I want A inverse first, of course. So I'll hit enter right on that. It'll give me the A. To get the inverse, I hit the inverse button, and then times. Probably don't have to put the times. Now I have to reference B, so I have to go back into matrix, second inverse, stay on names, and I'll go down to B and get it. And when I hit enter, son of a gun, there's your answer. So that's how to do it. Now another application of matrix multiplication and inverses is encryption.
As always, should you be caught or killed, the secretary will disavow any knowledge of your actions.
Remember what encryption is? Or have you ever seen it?
Sinister forces are at work.
Who would use encryption? It's kind of like coding. Who would use it other than secret agents? Okay, secret agents use it too. Anybody that wants to hide anything or keep it safe. Banks, phone companies need to keep your information safe when they send it. Any government network needs to keep all that information safe, so they use encryption. Cable TV providers don't want people stealing their signal, so they use encryption. Any type of private agency will encrypt its information. Now, what do we mean by encryption, and what does it have to do with matrices? That's what I want to show you. Consider this decoding, very simple decoding set of letters and numbers, and how they might represent this secret message. Okay? The message is going to be, if you can read it across, I'm in a flanked 2 position. Okay, just a crazy little message. And you would like to send that message to someone, and only that person can get it. Even if somebody intercepts it, we want to encode it or encrypt it so that the person that intercepted it could never tell what it was. Well, if we represent this message with the numbers, it actually equals this matrix. I'm going to call this matrix C for code. Now, you don't have to be a genius decoder to decode this matrix, okay? You know, figuring out that A is 1 and B is 2 and C is 3. It wouldn't take a real decoder very long to figure out what this message is. We would like to encrypt it. Well,
Excuse me?
I'm going to take this matrix, the code matrix, and I'm going to multiply it times a matrix that only I and the receiving message getter have. And these are just arbitrary, crazy numbers. And actually, these numbers are pretty easy. I could have picked some horrendous decimals and had them stored in my calculator and in my computer, as well as in my receiver's, my partner's computer. Okay, so you need to understand that this, while somebody might intercept the message, only the sender and the receiver have this message, this encoder message, this E message. That's the idea, you see.
Oh, man.
Okay, well, I'm going to input this into your calculator. I want you to do it. Now, if you've put it into your calculator, you should be able to tell me what is C times E. Anybody could do that, couldn't they? Well, even the person sending the message could calculate what C times E is. And believe it or not, that's what they would send. That crazy group of numbers, C times E, they would send this result to the receiver. And the The receiver would receive a nightmare group of numbers. That's good, though, because if somebody intercepted the message, all they would get is a nightmare group of completely random, arbitrary, what appears to be completely random, arbitrary numbers. Okay? Remember, though, that that receiver does have the E matrix somewhere stored on their computer.
Oh, will you help me? Can you help me?
Well, if they have the E matrix, they can also, the encoding matrix, they can also figure out what E inverse is, can't they?
Hey, wait just a minute.
So the receiver, and only the receiver, could then type on their calculator C times E inverse, which they have available to them because they know E, and what would happen? Those two would cancel out, and they would have
How sweet it is.
they would have the original code, which they could then go backwards and figure out what the message was.
Perhaps I could be of some assistance.
Well, everybody has that, and this is a very basic code, but it can be encrypted so that no one could figure out what it is.
Believe it or not.
Just like your cable television can be encoded so no one can figure out what it is, or your telephone calls can be encrypted so nobody can tell what they are. Only the person that has that magic matrix, and of course the availability to the inverse of that magic matrix, can actually figure out what the code is. And that's the idea and the strength of matrices and matrix inverses. All those numbers.
And now for something completely different.
Okay, I'd like to show you another application of matrices. They're somewhat related to probability, and they're called Markov chains. Much easier than what we've been doing, believe it or not, so you should relax. Consider this set of information about the probability of the weather. If it rains today, there's a 60% chance that it's going to rain tomorrow. Usually tomorrow is just like today. Usually. If it does not rain today, or if it's sunny, there's an 80% chance that it will be sunny or not rain tomorrow. Well, this is called transitional probability data. When we're talking about going from one state, that state being raining or sunny or happy or sad or whatever, to another. Okay, it's used to predict the future. Now this very simple data can be represented in various ways. I'm going to give you 4 ways that we could represent it, just so you'll understand it. One way is to do it in a table of transition probabilities. Okay, we'll represent the state of raining with an R and not raining with an N. So the transition from today raining to tomorrow raining was stated very clearly in the data is 60%, or 0.6. And the other state transition, to go from not raining to not raining, is stated very simply as 80%, or 0.8. Now we can fill in the probability of going from raining to not raining using the theory that probability is all the probabilities add up to 1. So it's either, when it rains, it's either going to rain the next day or not rain. Well, 1 minus 0.6, that has to be 0.4. And to go from not raining to not raining is 0.8. So to go from not raining to raining will be 1 minus 0.8, or 0.2. Okay, don't forget, all the probabilities that can happen in a sample space add up to 1.
Could it be?
Now, another way to represent this is with a tree diagram of the same transition probabilities. Now let's take a look at this with a tree diagram. The transition from a rainy day to another rainy day has a 60%, or 0.6 chance of happening. The transition, as they state in the data, to go from a non-rainy day to a non-rainy day is 0.8. Now we just subtract from 1 to get the other numbers. To go from a rainy day to a non-rainy day is 1 minus 0.6. And to go from a non-rainy day to a rainy day is 1 minus 0.8, isn't it? So that's another representation. And then, of course, we could branch off from those and do another day, perhaps. Yet another way to represent this is a node diagram, and you'll see that as well. These are nodes, the rain node and the non-rain node. Now this type of diagram uses circles and arrows. We'll represent the transition from rain to rain with an arrow from the rain circle back to the rain circle. And the transition from non-rain to non-rain with a 0.8 with once again an arrow from the non-rain circle to the non-rain circle. Now to go from rain to non-rain, we know once again that it's 0.4, 1 minus 0.6, so we're actually drawing an arrow from the rain node to the non-rain node. And to go from non-rain to rain, it's very simple again. We're going to go 1 minus 0.8 or 0.2. So you may see pictures like this that are called node diagrams.
That's the fact, Jack.
Note that all the arrows leaving any node have to add up to 1. See how the 0.6 and the 0.4 add up to 1, and the 0.8 and the 0.2 add up to 1, because they really cover everything in the sample space from that node. Okay, now that was 3 possibilities.
Here's someone who can help you.
We have one more very useful representation of this data. And that's going to be a transition matrix, your old buddy. Remember what a matrix looks like, rows and columns. Okay, so in this case we have the row for rain and the row for non-rain and the column for rain and the column for non-rain. So to go from rain to rain, we know there's a 60% chance. And to go from non-rain to non-rain, there's an 80% chance. And once again, all the possibilities have to add up to 1. So to go from rain to non-rain will be a 40% chance. And to go from non-rain to rain will be 1 minus the 0.8 will be a 20% chance. Once again, note that all the rows, which covers all the possibilities in the various sample spaces, have to add up to 1.
I know that, dude.
Okay. Well, now
Throw me a frickin' bone here.
we got to start asking,
Need the info.
which of the 4 methods is going to be the most advantageous representation when we want to start doing more difficult problems? Well, let's start doing more difficult problems. Let's start chaining these states together. That's what's going to happen. We're going to go more than one level kind of a thing.
Allow me to demonstrate.
For instance, consider this. We already know this. If it rains today, there is a 60% chance of rain tomorrow. And if it doesn't rain today, there's an 80% chance that it won't rain tomorrow. We already had that stored. Now we want to take that from a Thursday to a Saturday, meaning that if it rains on a Thursday, what is the chance that it's going to rain 2 days later, 2 days later on a Saturday? So we're going to have to chain 2 levels together, I hope you appreciate.
Perhaps I could be of some assistance.
Well, let's consider the tree diagram of this first, okay? One of the reasons I want to consider that is it shouldn't be too tough because
Yoink.
to go from Thursday to Friday anyway, I already have, remember, I already had that worked out. To go from rain to rain, it was 0.6, and from rain to non-rain was 0.4, and from non-rain to non-rain was 0.8, and from non-rain to rain was 0.2. So I've already got that worked out. And in fact, they say in this problem that it's starting with rain on Thursday. So I really only need to look at the half of it, right? I'm starting with rain on Thursday. So I have a 0.6 chance that it's going to rain on Friday and a 0.4 chance that it's going to not rain on Friday. Now I have to go one more level. Let's see. If it rains on Friday, then I can go use my 60%, 40% chance to get to Saturday. And if it doesn't rain on Friday, I have to go to the 80%, 20% chance for a non-raining day. Okay, now I've taken this tree diagram out from Thursday to Saturday, but I have to answer the question. If it rains on Thursday, what is the chance of rain on Saturday? Well, let's look at all the probabilities using a multiplication principle. If I go from rain to rain to rain, what's the probability that that's going to happen? Well, that's 0.6 times 0.6, or 0.36 for the whole chain. If I go from rain to no rain, that's going to be, isn't it, 0.6 times 0.4, or 0.24, that sequence or chain will occur exactly in that way. Now let's go from rain to no rain to no rain, and that'll be 0.4 times 0.8, won't it? Or 0.32. And lastly, rain to no rain back to rain. I'm suspecting that doesn't happen very often, and my numbers verify that. It's 0.08. Now remember what we're asking. The chance of starting off on rain on Thursday, which I did, and finishing with rain on Saturday. Now only two of these finish with rain on Saturday. Only two. This one, the 0.36, and this one, the 0.08. So I guess I'll add those two probabilities and I'll get my answer. So if it rains on Thursday, the chance of rain on Saturday, 2 days later, is 44%. That's how I would use a tree diagram to do it. And that's, consider that that's only a 2-day chain, okay? Well, let's look at it with a transition matrix. Once again, we want to go from Thursday to Saturday. Remember our transition matrix was the 60% and 40% and the 20% and 80%. Okay? It's all lined up for us. We had already done it a couple problems ago.
Why does this keep happening?
Well, in order to use the matrix, you're going to have to input it. So let me go ahead and input it into the calculator. Let me turn this baby on. Now, I'm going to input this as matrix A, but I'm going to be calling it matrix T. I hope that's not confusing. T for transition matrix, okay? But since the calculator doesn't go up to T, I'm going to have to choose one, and A is the easiest. So let me put this bad boy in. I'll go second inverse or matrix, and I'm going to edit. So I'll cursor over to edit, and I'll select A with enter. And this one is a 2 by 2 matrix, so 2, enter, 2. And let me put in 0.6, enter, 0.4, enter, 0.2, enter, and 0.8, enter. Okay, there's my matrix, so I'll quit out. Second mode or quit. Now, why would I do that? Well, quite easily. Couldn't I reference that using matrix names? And in order to find out what this matrix would look like 2 days later, guess what?
Hey, Doc, wait. I want to ask you something.
I can find out what T or A squared is by referencing the name and then hitting the squared button. And you know what you get? Recognize any of those numbers?
Does this answer your question?
How sweet is that? Notice we're going from rain to rain over a 2-day, the squared, time. How cool is that? You did have to go to a little bit of extra work to input it into the calculator, but that extra work is going to be is going to pay off big time.
Hold on, little fire, Scarecrow.
Because let's look at this one. Same information. We've already input the matrix. If it rains on Thursday, now I'm going to ask you, what is the chance of rain on Wednesday? That's the next Wednesday. Holy moly. That's 6 days later. Imagine
You've got troubles, Mac.
trying to do a tree diagram 6 levels far. Holy go to war. But
Perhaps I could be of some assistance.
now that you've input the matrix, I call it T, or on your calculator A, you can figure out what T to the 6th is, just doing to the 6th power. And you've got yourself quite quickly
We went from good to sensational.
an answer with very little calculation on your part anyway. Okay, so I think that the matrix is the way to go. And another nice thing,
I'll be back.
remember now, if you hit second entry, you can get, without even going into matrix names, you can get your previous entry and you can edit it and do various other questions
Plastic machine, Spock. You can't argue with
that you can't even argue with. You can figure it after 3 days, after 5 days, after 10 days. Okay, and you don't even have to go into matrix again using second entry. Now, when we start raising it to a lot of higher powers like 10 and even 6, I would warn you,
You look marvelous.
don't forget about your mode 2. That's the way you would set the decimal places, because these decimal places can get quite large. Okay, if that's what you want, fine, but you want to be able to work with it. Okay, so you've got a huge amount of power here now that you start using transitional matrices. Just in case you don't believe me, let me put this in. Let's see, we're going to go second, inverse, and we have that 2 by 2 matrix, the original transition matrix. So I want the name A, and all I need to do is square it. Now you can use this button squared and hit enter and get son of a gun, you'll get that answer. But if I wanted to raise it to the 6th, I can't use that squared button, so I have to go, in fact I'm too lazy, I'm going to go second entry, okay, and then I'm going to backspace and delete on top of that, and I'm going to raise it to the 6th power. So hit this button here, the exponent, to the 6th power, and son of a gun, I can verify my answer here. Now my answer here is rounded to 2 decimal places. Let's do just that. Okay, remember how to do that? We're going to go mode. I'm going to go down and only show 2 decimal places. Okay, now let's clear out. Now let's do the same. Second entry, A to the 6th, and you can see that I do get to 2 decimal places the same thing. How cool is that? Now you can show it out to as many decimal places as you want, of course, but I think it's easier to deal with maybe 2 or 3 decimal places. Okay?
Now then, boys, we'll see how much you learn.
Okay, let's try a word problem. A study at the University of Maryland showed each year 10% of engineering majors changed to liberal arts, 5% changed to business, and the rest remain in engineering. Okay, 3% of the liberal arts majors changed to engineering, 15% changed to business, and the rest stay in liberal arts. And then we've got the information for business students. 5% of the business students changed to engineering. Notice all the changes that are happening here. 8% changed to liberal arts, and the rest remain in business. Okay, that means we'll subtract from 100% when I say the rest. Well, the question is, what percent of the current engineering students will change to liberal arts 3 years from now? You'd like to be able to predict 3 years from now. If you could do it for 3 years from now, you certainly could do it for 4 years from now or 10 years from now. Okay? Hopefully you smell a transition matrix here.
number.
Once we have that transition matrix, we're going to be able to answer what percent of any type of change, if we can read it properly. For instance, in the second question here, what percent of the current engineering students will remain in engineering 3 years, 4 years, even 5 years from now? Okay, let's see. We've got engineering, liberal arts, and business in both directions. Now, let's start putting numbers in. This 10%, what is it again? It's the engineering majors changing to liberal arts. Engineering majors changing to liberal arts. There you go, from E to L, okay? Now this is 5% of the engineering changing to business. Engineering changing to business, that's 5%. Now how are we gonna figure out engineering to engineering? Well, we're gonna subtract that 10% and that 5% from 100%, and we'll get the remaining 85%. Okay, so we got 2 more rows to fill in, and once we have the transition matrix, as you remember from the last problem, we've got quite a lot of power. Okay, let's talk about liberal arts majors. 3% of them changed to engineering. So from liberal arts to engineering, we're looking at 3%. Okay, do a little bit at a time so you don't get overwhelmed here. Any more liberal arts information? The 15% of liberal arts changed to business. So from liberal arts to business, I'm at 15%. And the liberal arts to liberal arts, or the ones that remain there, are going to be 100 minus the other 2, isn't it? 100 minus 18%
Excellent.
is 82%. There we go. Now let's get that last row with business. 5% of the business students changed to engineering. Let's see, from business to engineering, 5%. And there's one more number up there. 8% go from business to liberal arts. Now we have to figure out that last number. Do you remember how to do it? Once again, you're going to subtract that from 100%. So subtract 5% and 8%, or in other words, subtract 13% from 100%.
Alrighty.
And now we've got a transitional matrix. We're ready to rock.
Nerd alert!
By the way, looking at transition matrices, you should know that the diagonal from top left to bottom right, we're going to call the retention values. Look at what numbers that includes. The people that went from engineering and stayed in engineering, the people that were in liberal arts and stayed in liberal arts, and the people that were in business and stayed in business. And that's going to be a common thing to look at. So when we ask you to look at the retention values, see whether they're high or low, it appears, at least in this one, they're relatively high. They're in the 80 percentiles. Okay, so that's kind of an interesting little tidbit. Now, we can't really use this matrix until what?
Now I use my secret weapon.
We're going to have to input it into the calculator. So let me do just that. Now, once again, let me remind you, I'm going to input this as A, even though I'm going to call it the transition matrix, the T. Do it with me now. You should be good at it by now. I'm going to turn this baby on and go second inverse, and I'm going to go over to edit, and I'm going to overwrite my other A because I'm done with him for now. So I'll hit enter, and this one is of course a 3 by 3, so 3, enter 3, and it makes some nice room for me. Now see if you can stay up with me. I'm going to go 0.85 for the first number, enter, and it'll naturally move across for me. 0.1, enter. 0.05, enter, and that's the first row. Now the second row. 0.03, enter. 0.82, enter, and 0.15, enter. Now I'm into the third row. 0.05, enter. 0.08, enter, and 0.87, enter. Let me check myself. See that they're all, and I see that each row adds up to 1, doesn't it? 0.03, 0.82, 0.15. I'm looking good. So let me quit out, and now I've got the power, don't I? Second mode is quit. Okay. Now what am I going to have to type to basically predict the future here 3 years from now?
Certainly.
I'm going to use matrix names and put in t to the third. And I'll get, I promise,
The important thing is it your final answer?
I'll get a matrix like this. But is this my answer? Now, wait, let's take it one question at a time. What's the question? Question is, what percent of current engineering students will change to liberal arts? So I want to go use my t to the third, my transition to the third, and I want to go from engineering to liberal arts. And there's your answer. Now I do have another question. What percentage of current engineering students over the 3 years will remain in engineering? Well, let's see. We're going to go from engineering to engineering.
You're absolutely correct.
And there it is. Okay, we've done it over 3 years. Pretty cool, huh? Okay, let's do just one more for practice. This was an interesting one. You know, in professional sports, teams get on streaks. And records show that whenever an NFL team wins 1 week, there's a better than a half probability that they're going to win the next week. In fact, there's a 0.6 probability that the team will win the following week if they win 1 week. If they lose 1 week, the probability of losing the next week is 45%. Kind of weird, isn't it? Anyway, let's ask this question. If the Redskins win this Sunday, and I don't have tickets for 4 more weeks, what is the probability that they'll win 4 weeks from now when I do have tickets? Well, we have to create a transition matrix. We're going to go from win to win to loss, and all the possibilities. Well, to go from a win to a win is a 60% chance. Now I know 1 minus 60% is going to give me to go from a win to a loss. So I can put that in. The other number they give me is to go from a loss to a loss. 45%. And I once again can get my other number by subtracting from 1. Now, if we take that transition matrix and I will need to figure out the probability 4 weeks from now, well, if I find out what t to the fourth is, it'll give me a semblance of my answer. I have to know which number to use. I want to go from a win to a win. And you can see that it looks like the chances are 58%, given that I won this week, that I'll win 4 weeks from now. Not very good chance, actually, I would say. Anyway, you get the idea how you might use this. I want you to go practice it with the homework. Dig in.